so we've chosen to map from D to S, okay, and this function here, we know it just maps vertex numbers, you know, vertex 1, vertex 2, vertex 3, into other vertex numbers via this function. So that's a mapping of 1 to phi of 1, 2 to phi of 2, and so on. Right? Okay, so we know what phi is. Right? It just maps the vertex numbers into. So in effect, it's mapping the set 1, 2, 3 into the set 1, 2, 3, where the numbers 1, 2, 3 are the vertex numbers. Okay. Now we're mapping to S3. Right? Now what is S3? S3 is the set of permuters. It's the set of permutations, if you like. So it'll be of this form. Right? Remember the bracket notation. So if we're mapping to S3, we're mapping an element. This phi is an element of D3, and we're mapping that into another element, right, of the second set. Now this is a permutation. This is the set of permutations. So the element here needs to be a permutation of some sort. So it'll be of this form, you know, 1, 2, 3, and whatever. So here's the suggestion. Here's like a critical part of the proof. Let's map this element of D into an element of S in the following form. So this is now a permutation, right? It's in the bracket format of a permutation, right? So now this is a permutation and of 3 objects. So object number 1 gets mapped to phi of 1, and 2 to phi of 2, 3 to phi of 3, which is sort of very similar to here. So you begin to see why these two groups are isomorphic. This is a permutation, and the phi here is a mapping of vertices. Okay, all right. So we've chosen our mapping. Seems to make sense, you know, because that's a well-formed permutation. You know, it's in bracket form. Now, okay. So now let's try to prove bijection. Try to prove that this function f is bijective. And remember, God, how many times did we do that? 3, 4, 5? Let's count. In the previous lecture. So to prove that this f is bijective, you have to show that it's injective and surjective. Right? Now, I'm not going to explain that again. Done it so many times. All right. Now remember the standard proof to show that the function this f is injective. You just take 2 arbitrary elements of so these are 2 elements of D3, okay, and we then just choose 2 elements from S of 3, so they'll be of this form, right? So f of phi, and you let it be equal to f of psi. Right? You just you know the usual thing, right? You're mapping from here to here. You take 2 arbitrary members of your codomain. You assume they're equal, like this, right? And then you prove that the 2 elements that mapped. So if this one maps to that one maps to that one. If you assume these 2 are equal in value, like this, then and then if you can prove that that one and that one are in fact the same, they're the same element, that's your proof that this function is injective. You've done that quite a few times. All right. Okay, what is phi, f of phi? Well, it's just this, right? So just write that there. And what's f of psi? Right? Phi and psi, both Greek letters. Those of you, the next, not next lecture, but next lecture set, the next course after this one on finite groups at undergrad level, senior level. When that's finished, the next course, lecture set, I will do will be on senior level, because I'm doing all the undergrad courses first. Senior level quantum mechanics, right? And you will definitely see this symbol appearing a lot. It's the so-called psi function, which is famous in quantum mechanics, associated with the name of Schrödinger, Schrödinger's psi function. Okay, all right. So you let these two be equal, so let that equal that, so this will equal this, right? So if you put a psi here, we get a psi here, all right? Now these two are equal. Therefore, this equals that, that equals that, that equals that, and therefore this permutation is the same as this permutation, right? They're the same. Therefore, it's injective. Okay, this mapping F is injective. All right. Now, once again, at the risk of being tedious, go back to theorem 27 on page 76 of your text, and you may remember that theorem. We keep using it. If the size of your two sets are equal, and in this case they are, right? This is size 6. There are 6 symmetry operations on an equilateral triangle, and the symmetric group with n objects is, well, you can just see it's 6 members, right? So the size of these two sets, in fact groups, is the same. Okay, so the bar like that just means the size of. Okay, so the size of these two sets, or in this case groups, are equal, and both equal to 6. All right. Now theorem 27 says if the size of your two sets you're mapping between, if they're of equal size and you've proved that mapping is injective, therefore it's surjective. And theorem 27 also says if the size of these two sets are the same and your mapping between them is surjective, therefore it's injective. So in other words, if the sizes are the same and you have one of these, if it's either injective or surjective, then you have both. And if you have both, by definition, it means that your mapping is, what's the word? Bijective. You know, bi, two, has these two conditions. It's both injective and surjective. It's bijective. All right? Okay, now, okay, so we've proved that this F is bijective. Now we have to prove that, this Fmn thing, where is it? Where did I write it? Yeah, now we have to do this thing to show that the elements, the corresponding elements in the two group tables map also. All right? Now, in the text, he does it the other way around. Instead of starting this way, f of mn, he starts f of m times f of n and proves that to be equal to this. Right? So it's going the other way from what we were doing typically in the past. Going one way or the other way, if they're equal, it's fine. All right. So now have a look at this, and have a look at this. Now, can you remember me saying, previous session on pictures on this board? Here's a pair, right? Here. Object 1 maps or goes to phi 1, and 2 goes to phi 2. These are just they represent numbers. They're 1, 2, or 3. Yeah? So this whole thing is a permutation. But look, I could take this pair and swap them around. It's still the same permutation, right? The ordering of the pairs. I mean, I could have 1, 3, 2, 3, 2, 1. So long as the vertical pairing remains the same, because that's what the permutation